Okay, let's look at question 4.3. 4.3 asks us to implement an entirely different iterative improvement algorithm to find the local minimum of a function, and that algorithm is known as gradient descent. Now, just before we start, I just want to say that this particular algorithm, of course, will not be on the exam. What is important here is that you understand the procedure that you should go through to implement any iterative improvement algorithm. Okay, so what gradient descent does intuitively is it basically picks a point on some random point, as the starting point of the function, and it uses the derivative to find what direction the minimum must be at, and it just takes a small step alpha in that direction at every iteration. So this is the update equation for gradient descent, and whenever we ask you to implement an iterative improvement algorithm, you can always expect to get the update equation and also the terminating condition, which was question 1. So given all of this, implement gradient descent. Okay, so let's do that. Alright, so gradient descent, the algorithm has two parts, or any iterative improvement algorithm has two parts. We have to implement the update function, which I've called gradient step here, and the check for the terminating condition, which I've called gradient done. And this is just a function that'll wrap a call to iterative improvement, just like this find root function did for Newton's method. Okay, so let's do gradient step first. Actually, before we get to that, let's look at this hint. So to check for the terminating condition, which by the way, the terminating condition is this thing right here, that the difference between the two x's, the old x and the new x that you've just updated using this x, is very small. And in order for you to do that, you basically need to remember both of these x's. So in order to do that, we're just going to use a guess that is a pair, and we're going to update this pair like this. Right, so this is the old pair, and we're always going to say that the second element of this pair is the current value, and the first element is the value that is one iteration old. So if we take this pair and we find the next update, if we call it x prime prime, then of course x prime now becomes the new value that is one iteration old, so that gets put in the first element of the pair. Okay, so that's why in the gradient descent function here, the guess starts at none and then 1. Okay, so we're going to start our guess at 1, and at our first iteration, we don't have a previous iteration value for x, so we're just going to use none. Okay, all right. So to perform the gradient step, we basically have to implement this equation. So let's look back at Newton's update. Right, what Newton's update did is it defined an update function that implemented the update equation that we have to use. So let's do the same thing here. What we have to do is to say def, right, define, let me delete this pass here, define this update function that takes in some value guess, okay, and again this guess will be this tuple, okay, and let's ignore the body first and return update. By the way, this is sort of the procedure that I always follow when I write a higher order function. I decide the arguments that the function needs to take and what structure it needs to have, and I sort of ignore the body in sort of my first pass at the question. Okay, so now what we need to do is we need to get the current value x out of this guess. Now we said that the current value is going to be the second element of this pair, so I'm just going to call this current, okay, and it is going to be the first element of my guess. Okay, now after that I can just implement this update equation, return, okay, something will go here, and the most recent value, which we said is always going to go in the second element of our guess, is this update equation, current minus alpha times approx derivative f at current. Okay, so then now that we have our newest value, what is our old value? Well, if this is the value that we updated from current, then current has to be our old value. So I'm going to call this current. Okay, so that's it. That's our update equation. And the gradient done function is similar, just like the find root function, which is presented as a lambda here. But the concept is basically this gradient done function needs to return a function that checks to see if the algorithm should terminate. So again, we have a higher order function, so I'm going to call this done. It takes a guess that it needs to check, ignore the body, and it needs to return done. Okay? Alright, so what should be the body of this done? Well, what we need to do, again, is to check this condition here. Okay, so what we need are the new and old values. So let me just get the old value first. Okay, let's call it before is the first element. Actually, I can just say before comma after equals guess. Okay, and this gets the first and second element out of the guess pair. And the first thing that I need to check actually is that I've actually performed at least one step of gradient descent. And that is because I started this pair at none, and what we want to do is at least perform one iteration. So what I need to check is to say if before is none, then we want to continue the algorithm, so I should return false. If before was not done, then that means that, if before was not none, then that means that we have to perform a check to see if we're done. So that means that I should return that the absolute value of f after minus f before, close the absolute value, has to be less than the size, which I've put here is 10 to the negative 6. Okay, so this line right here, this absolute value inequality implements this line. And here, instead of saying equals to 0 exactly, since this is an approximate algorithm, we've just said that the difference is less than some very small number. Okay, so those are the update and the termination check. And all we need now is to simply call the iterative improvement algorithm, which is called iterimprove. And the update function is the gradient step of f. The termination function is the gradient done of f. And of course, we want to start at the guess. Okay, so this is most of the algorithm. There's one tiny detail left, which is that since I've arbitrarily introduced this concept of my guess being a pair of an old value and my most current value, that means that when I return this, I need to sort of undo that assumption that I've made, right? So what I need to do is get the most current value out of this iterimprove return, which of course is my second value. So that should be the gradient descent algorithm. So again, I can get my terminal, I can import this file, and I can say gradient descent. Let's do the same function there. X minus 2 times x minus 2. Okay, and again we get a value that is very close to 2.